Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about NeutronStar. So let's dive right into it. Well, first we have to understand what the heck we are talking about. We are talking about a dead star. So basically dead star, once the stars die, they generally have three states. Black hole, which we have already covered, white dwarf, which we have already covered. This is the last stage, neutron star. Now, neutron stars are creation of a star. Now, generally stars death is directly controlled by stars mass. Basically, if a bigger star goes boom, it has a different outcome versus a small star going boom. So all of that is directly controlled by how massive it was. So generally, for simplified reasons, people generally classify for making a neutron star, like as a would your star corps will become a neutron star, you have to be at yellow star or blue giant. Basically, you have to be big. That's the starting point. You have to be big and huge in order to become basically this neutron star thing. Now, generally, to give you a context of that, what kind of density we are talking about, white dwarfs are very dense because they are literally like a star, like a sun at the diameter of Earth. So basically you take YOLO amount of diameter and you compress it into Earth size. Now still it's a celestial object. It's still like, bigger than moon. It's like planets. It's like, above human comprehension normally. But this puppy comes inside human comprehension. To give you a context of that, imagine our sun. It's big, it's huge, it's massive in terms of diameter, in terms of size and all that. In terms, it's huge, it's impressive. Now compress all of that puppy into under 50 kilometers. Let that sink in. Like something that massive, something that powerful compressed inside 50 kilometers. It's on a different level. Basically, if you take Earth, white dwarf, you will have hard time seeing neutron star. It will be so small comparatively speaking. 50 kilometers, that's something that you can understand. Like, and not to mention 50 kilometers, like I'm telling you the biggest limit I have even heard. Like most people are saying like it's barely 20 kilometers or 30 kilometers. So it's tiny compared to speaking. Like as a celestial body, in terms of density, in terms of gravity, like it's almost at the level of a black hole. Basically, it even have some signature of black hole, which means you can see more than 100%, basically 50% of its surface. Why? It's bending space and time, literally. Like any more, it's black hole. That's the whole point. Like it is at the second basically density level. First is black hole, because black hole is like YOLO. It's like I collapse space and time. So black hole is there. Then you have neutron star. Then you have white dwarf. So this is what we are talking about. Now, what do I mean when star dies? It's rather very simple. Star is generally a nuclear fusion engine. It runs out of fuel, it goes boom. So why the heck it goes boom? Well, star has mass. That mass ignited fusion in the first place. So it reached an equilibrium place where it's like, fusion is pushing outwards and gravity is pushing inwards. Now you have to be mindful. You will run out of fuel, but you will not run out of gravity. If you have mass, you will never run out of gravity. Gravity does not have an off switch, or it does not have a decay limit. It's like infinite. Like infinite as in terms like how long it will apply. It will apply till infinity. So fusion runs out. Like basically you have fuel, you take hydrogen, you convert it to helium. You take helium, you convert it into something heavier like oxygen. Then you take oxygen, you convert it into something heavier like carbon or iron. By the time you reach iron in periodic table, the end. Basically you cannot fuse iron and get energy out of it. So done, game over. And then star collapses. Now that collapsing generally is opposed by many things. Again, you are still talking about matter and you have to collapse it. Now stars are generally in plasma size, so they are not very dense. However, even in normal star, their cores are very dense. Now you're trying to collapse that puppy, it goes a young, bonkers. At that point, electron says, you shall not pass. Now this is if your star started at like light enough, it will like electrons are like, bro, you shall not pass. Like, bro, you cannot pass me. And that point, electron degeneracy pressure would be like, no, you will not collapse any further. And that's why you will have white dwarf. But what if your starting mass was much higher than it? At that point, electron will fail. What will happen after that? Electron will go to proton, get married, and become a neutron. Again, I'm simplifying. That neutron will go into atom and collapse with another neutron. To give you a context of how significant that is, most of us is 99.99% empty space. Because if you take an atom, you expand it to like large human scale. Let's say it's like a golf ball in a center of a stadium. The electron is basically outside of the stadium. That's how empty a normal atom is, most of the universe is. And this is what gravity is collapsing every matter, like every single atom is trying to do, and collapsing it into a central place. That's why the fact that there is proton and electron is like, bro, we cannot handle this. They are collapsing into nucleus and neutrons becoming into neutron. Then that neutron is going into another atom's neutron. So basically all you have is neutron. You are no longer in a place where you have any electron shell. All electron shells have been stripped apart. So that's on a different level. At that point, another force start to apply, and that's neutron degeneration. When neutron is like, bro, you shall not pass. At that point, neutron is strong enough that it can like, okay, I can hold it, and some other repulsive force is also acting, and that all of them combined is like, no, You shall not push me any further, because if you put any more mass, it will go black hole. So that's how it is made. And not to mention, if you take a neutron star and you want to basically weight it up, 99% of it is neutron. So basically, neutron in the core, outer shell is just the electrons that survived and all that jazz, but core, raw neutrons, raw neutron and nucleus. And at that point, the quantum physics starts to take over, and quantum physicists have come with very interesting names. I would urge you to type what is the names of matter found in neutron star. They have spaghettiest name. A lot of spaghetti is there, because at that point, at that density, quantum physics starts to take over, because like two nucleus should not be that close to each other. It only happens in a neutron star, and outer electrons and all that is there. So it almost becomes like a planet. It has a core, it has a crust and all that jazz. So that's what happens in a neutron star. Now, because neutron star was a star at some point in time, and most star, or almost every star, has some amount of spin. It could be slow spinning. It would be like, one rotation in 7 days, or one rotation in 300 years. It will have some rotation. But because you took something super massive, as in let's say blue giant, and you collapse its diameter into, let's say the diameter was 1, you collapsed it into 0.00000001, physics start like, bro, you should follow the rule of conservation of angular momentum. What does that mean? That simply means when you see ice skater, they are spinning, let's say they are spinning at 10 rpm, and they collapse their hand like this, they will go to, let's say, 30 rpm, because angular momentum must be conserved. Same applies to a star also. And star went from the gradient, basically how far it was, how big it was, what kind of rpm it was, how much you collapsed it, the rpm becomes YOLO. To give you a context of that, the rpm is so powerful, so high at certain places, certain neutron stars, the outer surface could be traveling as high as 25% of speed of light. Let that sink in. It's not kilometer per hour, it's speed of light. It's 25% of speed of light. So that's kind of RPM we are talking about. It's YOLO level RPM. So, and this also helps prevent the star from collapsing into black hole, because there is centrifugal force that's it pushing outwards. Because if it was spinning any faster, it will actually fall apart. Gravity will be like, I can't hold this. That's the spin. That's why spin is so important for a neutron star. Now, because you have something spinning, you have something hot. It was a star after all, so it's a very hot thing. It is very high spinning, and it has an electron kind of traveling outside of. What does that mean? It's basically world's biggest dynamo. It's YOLO amount of magnetic energy is there. So magnetic fields that is created by this puppy is on a different level. Like, we cannot even tangibly measure it, because Earth has a magnetic field which is not very strong, but it is huge. Basically, in terms of size, it's huge, but in terms of Tesla, it's not that great. Like, we have MRI machine that's much higher than that, 3 Tesla, 4 Tesla, and we are working on Large Hadron Collider that should be upgraded to 8 to 9 Tesla. Different things. Sun, yeah, now we are talking. This puppy makes sun's magnetic field look like, bro, is there something like I'm supposed to look at it like the amount of zero you have to add in Tesla wise? It's ludicrous level. Basically, it reaches a point where the numbers are meaningless. Like 10 after 18 zeros. What? It's like it goes to ludicrous level. Now, because you have a magnet, you have a spin, the amount of energy converges into the pole, and pole becomes a giant particle accelerator. It's basically ultra supercharged, Large Hadron Collider, and that energy released in that pole's area becomes like a miniature gamma ray burst. Like, that's how powerful this puppy is. Like, at few light years, yeah, if it sweeps across your planet is gone. Like, there was no planet anymore. So the amount of energy released on those EM waves are huge. Basically, they go from X-ray, gamma rays, microwave, ultraviolet, infrared, everything is there. It's just that by the time it reaches, it's generally gamma rays is the only thing that survives, but we can detect it. Like, we have been detecting. That's how we are finding this out. And because of the spin, there is a effect known as lighthouse effect. Think of it this way. Let's say a lighthouse is there. You can see a lighthouse if the light sweeps across you, but will you see a lighthouse if it's sweeping like this? No. So every neutron star, to best of our understanding, have this kind of jets of stream coming out, but we do not call them pulsar, simply because pulsar is to us. Basically, is this star a pulsar to us or not? That's what matters here. So if we have a radio telescope, we are pointing at it, and its beam sweeps across us, and we detect a pulsar. If we don't detect it, it's like, yeah, it's a neutron star. It could still have that, but let's say alignment is not matching up, will not classify that as a pulsar. And in terms of what kind of pulse accuracy we are talking about, this puppy, when we first discovered it, we thought it was alien. Like, it was literally tuk, 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 tuk. It was idiotically precise. To give you the idea, tuks are how we describe time. Basically, you take your watch. What does it have? It has an oscillator. Or what is oscillator doing? Tuk, 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 tuk. Everything. You take an atomic clock. What is it doing? Vibrating the atoms. Atom is doing tuk 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 tuk. This puppy was idiotically precise. It's like almost as precise as our best atomic clocks. So it's on a different level. So we used to think like, it has to be intelligently done, but turns out it's just basically super high density star spinning very fast. So beam is going across us. Now, in early days, we used to think this will be a very good method of finding planets. Basically, let's say we become like Star Trek kind of civilization. How would we find where to go? This will act as our GPS satellites, and that's why the Voyager has a golden disk. That golden disk has an Earth's map, basically Earth's three-dimensional location based on pulsars, and each pulsar signal, basically because of the frequency, depending on RPM, each of them has a frequency. Let's say this is rotating at 500 hertz, this is rotating at 2 kilohertz. You have a certain thing like that. And at early days, we used to think that would be good enough for long enough. In technical terms, yes, it still is, but what we know now, they are not. They do spin for a very long time, but they do slow down. They are not infinite source of energy. They do slow down. What does that mean? That inherently means, so let's say we send that golden black and it survived for millions of years, the data would be inaccurate simply because the frequency would have changed. So still a very good system for a few thousand years, but not for millions of years. But we were very confident, like this is how civilization will use a next generation GPS, global positioning system. No, universal positioning system. But it will not work for that kind of time scale. It will work for a few thousand years, but you have to keep calibrating the data, because again, it does not have fusion anymore. It does not have an energy source. It's just conserving the energy. Now, when I talked about white dwarfs, they are very stable. Like, they are the best place to build a civilization. Let's say you want to build a Dyson swarm, they're the best place, because everything that would be violent has already happened. Nothing else will happen. It's just have a steady source of decaying energy, and you can calculate how long will it decay. Let's say you start radio civilization. At that point, the surface temperature was, let's say, 10,000 degrees. It's very cool at that point. That means it cooled down most of it. But if you calculate like how long the surface temperature will remain 10,000 degrees Celsius, like how close you have to be, it's a small thing. So you can orbit it. Like, again, we are orbiting, like ISIS is doing the same thing. So how long it will remain? It's millions and billions of years. So that's very stable, and nothing boom bam bidim will happen. On this puppy, it's on a different level. First of that, beam itself, it's very high energy. If it sweeps across you, you dead. If you are made of anything metallic close enough, the magnetic field is like YOLO, bro. But on top of that, because of the high spin energy, because of the fact that it has a crust, because of the fact that it has a core, it has starquakes. Yes, you heard it right. Basically, it has a fancy earthquake. So the amount of energy we are talking about sometimes goes on a different level. Like, just below black hole level, it reaches a magnetar level. Basically, once it was created, it was too energetic. Basically, the amount of magnetic energy, the amount of spin it has, it's too damn high. At that point, it's very dangerous. At that point, it's very dangerous. So the magnetic strength goes from a neutron star. Let's say neutron star has magnetic strength of 1. This puppy goes to 10,000. So it's on a different level, and it can destroy things light years away. That beam is almost as powerful as a proper gamma ray burst. At this point, it's just a miniature gamma ray burst, continuous gamma burst. So it's that powerful. But because of the high energy, high energy, it's dumping, it burns out quickly. Then, because of the surface, because it's so much energy is there, it cracks, same way our earth crust does. But because of the intensity we are talking about, because of the mass it has, the shock wave it releases it outside sphere. Basically, it has a fancy what we call coronal mass ejection. Now that oomph, the amount of oomph it generates out, think of it this way. That's how we know it happens. It happened few years ago, like as in humanity wise, few years ago, and we detected it 50,000 light years away. Yes, 50,000 light years away, a star sneezed and we figured it out. So if it happened any closer than that, we did. So this puppy is on a different level in terms of how violent this puppies can go. Like, we have to actually, once we start to cross a threshold of, let's say, 10,000 year, 20,000 year, we have to start analyzing every single neutron star, because if one of them goes boom in the wrong place at the wrong time, for us, yeah, we did, and we would not even know it. So this is on a different level. Like, the amount of energy it can dump, like, think of it this way, like our old ancient technology detected something that powerful happening 50,000 light year. It's a very, like, the destruction of these puppies are on a different level. Now, how does they end? Basically, white dwarf simply cools down. It's a very stable thing. It's a very gentle, gently going into the good night. This generally does the same thing, because again, it's just a star that died. It no longer has the energy, and the spin that is exerting, the magnetic field it's exerting, it's literally creating drag in space-time. So space-time is slowing down slowly, and gravitational wave is releasing. However, let's say if it does not cool down, what will happen? Most likely, most of the neutron stars that we know, they are generally in binary star. Binary stars are the common thing. So those two will orbit each other and then collapse, which you have heard recently in the news, because those collision events are such a high energy event, we can detect this gravitational wave. So It's a very cool slow down phase, but generally there is a chance that it will end up colliding with something else, and the moment that happens, black hole is created. Because again, it was almost as powerful as a black hole is, like little bit more push. It just needed that little bit push. So because of the time they are generally in binary star, it could also happen, it could have a healthy star next to it and neutron star, you know, revolving around it. But in those sort of scenario, revolving star will not last very long, simply because it's guzzling up matter from the main star. It will collapse early. Basically it will go to black hole early, and then it may end up collapsing the big star even earlier. So it has an end, and most of the time it will end as a black hole. So this star is not very good for colonization. Like white dwarfs, they are amazing. Basically they're small, you can create a Dyson swarm very reliably, and you can predict how many million and billion years you're gonna last. That's awesome. But this puppy, yeah, it's useless for us. So this was my presentation on NeutronStar. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me your disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.